Welcome everyone. Today we are going to see the introduction to the counter. Counters are the circuit which can count some events, the occurrence of the events. In digital electronics we have two types of circuits. One are the combinational circuits and another are the sequential circuits. I'm assuming you know the difference in combinational and sequential circuits, and counter is the type of the sequential circuits. A counter is a device which store, I will tell you why it will store, is a device which store the number of a time a particular event or a process has occurred. For example, I need to design a circuit for a digital clock, and we all know after 1 second 2 need to be displayed, after 2 3 need to be displayed, after 3 4 need to be displayed, and so on, because the next coming output is in the sequence with the previous output. So that's why they are come under the category of the sequential circuit. And the second thing, this counter is a kind of increment counter. It need to be increment 1 second in the previous value. So it has to store the previous value in some memory element. And we know the basic storage device in digital electronics is nothing but the flip-flop. So in the coming few minutes we are going to see how we can use the flip-flop to design a counter. If we look at the use of the counter in digital electronics, there are many uses, but specifically it can count the happening of any of the events. We can segregate the counter in different classes depend upon their circuit design and depend upon their use. Right now we are going to classify them into their uses. For example, we have up counter, as I already give you the example of the clock, digital clock, it is the up counter. A down counter which can count the number in the downward direction. Up down counter which can count in both the direction, in upward and downward direction. Random number counter, even number counter, and odd number counter. I hope you all have played any kind of racing game, maybe car racing, bike racing, and on the screen you are able to see many types of counters. So with the help of this picture we are just going to analyze what are the different types of counter we can see. On the top here, this will tell me the position, that in this particular race the 6 participants are participating and this particular participant is at the 5th position. Whenever during the race this participant will cross any of the vehicle, it means it need to be decrement. So this position become 4th, this 5 become 4th, it will decrement. And if some of the participant which is behind this particular participant cross this one, this particular value need to be increment. It means this particular participant has a position 6 now. So this can be an example of a up down counter. On the other hand side, this next thing is the clock, just telling me that how much time is already passed when the race has started. It's showing me 8 seconds something. Another example, whenever you can see there is a race on the side of the track, generally there are some big LCD screens are there on which they are displaying the time for a particular athlete, that how much time it is taking to complete that race. So there are many applications of the counter. One more example I can give you for up-down counter is, let's suppose you are going to enter in any shopping mall or in any event. In the main entrance, there is a metal detector. On the top of the metal detector, some numbers are displayed, and these are nothing but a type of counter. They are just counting that how many people have entered to this shopping mall and how many people have just left the shopping mall. So this is the basic introduction of the counter where we are using them. Now we are going to see a type of counter which is a 2-bit asynchronous counter. Later, what is right now this thing is 2-bit. 2-bit means I have only two numbers. Either I can write 0 0 or I can write 0 1 or I can write 1 0 and the last one is 1 1. So these are the 2-bit number in digital. So this 0 0 is equivalent to 0 in decimal, this is equivalent to 1, this one is 2 and this one is 3. So this counter can count from 0 to 3 and again roll back to 0. Again it can start from 0. This block is nothing but representing a JK flip-flop. These are the two input J and K, the output Q and Q bar. This is another flip-flop J and K, Q and Q bar. Why I require two flip-flop? Because one flip-flop can store 1-bit data and I'm going to design a 2-bit counter, so that's why I need at least two flip-flop to store that 2-bit data. To use this counter, I'm just simply going to use this JK flip-flop in the toggle state. It means I'm always connecting my J and K of the flip-flop with the high value. This high value will be 1 or VCC, that doesn't matter. Similarly, I'm going to use the second flip-flop also in the toggle mode only. J is 1 and K is also 1. The first flip-flop clock is going to be connected with the clock or the circle, maybe the oscillator. One thing is there, these flip-flops are a kind of negative edge table flip-flop. So there should be bubble and arrow. This indicate S, this indicate negative sign. Similarly, this one is also a negative edge table flip-flop. This is JK flip-flop. This can be here. This is flip-flop 0. This is flip-flop 1. This will be Q naught, I can say, and this I can say Q. Doesn't matter. It is mentioned here. Q naught, Q. We are going to understand the working of this 2-bit asynchronous counter with the help of this timing diagram. On the top, I have a clock. For 50% it is 0, for 50% it is 1. So from here to here, this is the one cycle. That is second cycle, it is mentioned, third cycle, fourth cycle and fifth cycle. So actually what this counter will count? This counter will count the cycle, that how many cycles of the clock have been entered. Now this flip-flop is a negative edge table flip-flop. It means we need to identify the negative edge in this clock. This one is the first negative edge which we have. This one is the second negative edge which we have. Then I have the third negative edge, then fourth negative edge, and the last one is the fifth negative edge. When the first negative edge occurred in the clock, at that particular time the input to this first flip-flop, which is FF0, this is the LSB, and this is the MSB. At first clock, when the negative edge occurs, the input JK is high, so it means this flip-flop needs to be toggled at this particular edge. So the value of the flip-flop Q0 initially is 0, so it will get toggled and show you the value 1. But at the same time, the flip-flop second will not toggle. The point is the clock input to the second flip-flop is the output of the first flip-flop, and the output of the first flip-flop is this one, because it will only toggle. This is also a negative edge table flip-flop. But this second flip-flop, the MSB flip-flop, will only toggle when I will get a negative edge in the output of the LSB flip-flop, like here. After the second clock, the first flip-flop will be toggle again, come to 0, and I will receive a first negative edge in my LSB output. Due to this negative edge, my flip-flop 2, which is MSB flip-flop, will toggle and show you 1. This process will continue and you can see the completion of the waveform. So if I'm going to analyze what's happening, how it is counting, in the first clock, my output Q0 and Q1 is what? 0 and 0. So 0, 0 indicating what? 0. When the first clock occurred, it means this flip-flop has count the first clock and it start displaying the values 0 and 1. LSB is 1, MSB is 0. And 0, 1 indicate 1. It means the 1 clock has passed. After the second clock, it's showing the status 1, 0. 1, 0 indicate 2. It means it count the 2 clock has passed through the first flip-flop clock here. After third clock, it start displaying the value 1, 1. So this is 1, 1, 3 here display. After the fourth clock, it need to be displayed 4, but I can't represent 4 with 2-bit representation. To represent 4, I need 1, 0 and 0. It means 3-bit representation is required. This carry goes on the next flip-flop where I don't have in the circuit, and my circuit again starts from here 0, 0. It draw that. So this is the simple working of 2-bit